Today we talk relations and functions, and you'll notice that I have for you a coordinate system. And in this coordinate system, we have two sets of what we call axes. The horizontal is called the x-axis. The vertical is called the y-axis. And if we talk about coordinates within this system here, our x-coordinate is the horizontal placement of any point, while our y-coordinate is the vertical placement of any point. When we talk about a relation is just a set of ordered pairs. So it's basically some xy coordinate. And when we talk about the domain, we talk about the set of all the first elements in this relationship, or an x-coordinate. When we talk about a range, we talk about the set of all the second elements, which is the y-coordinate. Sometimes what we do when we want to talk about relationships is we talk about mapping. And what I have in front of you is I have a relation made up of a set of points. And what we want to do is we want to write this relationship as a table, and then we're going to do a mapping on that relationship. And once again, a mapping is just an illustration of how the domain pairs with each element in the range. So let's do a table first. And in a table, it's basically an XY table where we list all the x coordinates. So in this case, I have 4, -2, 2, and 0. Then I list all the y coordinates associated with each of those x coordinates. So that's 3, 1, -4, and -4. And it's okay that -4 repeats itself. When I talk about a mapping, the mapping is very similar, except for the fact that you don't repeat the numbers. So here is our x box, if you will. Here's our y box. And I'm going to put each element of the x values in this box. So I have 4, -2, 2, and 0. And each element of the y values in the y box, but this time I will not repeat any of those y values. And now in order to show a mapping, what I do is I put an arrow going from each element in the x box, or in the domain, to the paired element in the range, or the y's. So in this case, the 4 goes to the 3. The -2 goes to the 1. The 2 goes to the -4. And you'll also notice the 0 goes to the -4. So it shows, if you will, a double pairing. If I want to determine the domain and the range of this relation, spelled that wrong. I find the domain by saying that is the set of values 2, -2, 4, and 0. When I talk about the range, it's a set of the values 3, 1, and -4, much like the map. No need to repeat those numbers. If I want to actually go ahead and graph a relation, that means graph these coordinate points. We know our first value is an x value and our second value is a y value. The x value is the horizontal placement, so I move over 3. The y value is the vertical placement. I go up 5, and there's the point 3, 5. I want to graph the y coordinate. I go 0 on the x placement, or horizontal, down -4 on the vertical placement, and that's the point 0, -4. -6, 2, we go horizontally, -6, vertically 2, and there's my final placement. Let's throw some more definitions at you. If we talk about an independent variable, that's going to be the variable that's going to determine the outcome, and it's also typically an element of the domain. When we talk about a dependent variable, it's the variable that depends on the independent variable. So that's going to be the y value, or what the output value usually is. So I've got a couple examples. Here's our first example. We say that in warm climates, the average amount of electricity used rises daily, or as the daily temperature increases, and falls as the daily temperature decreases. So we need to know what is being affected and what affects it. All right? Well, the average amount of electricity is affected by the temperature. So in this case, the electricity depends on the temperature. So the temperature is one thing, and the electricity is another. Electricity depends on temperature. So this here is the dependent. And this temperature is the independent. The number of calories you burn increases as the number of minutes that you walk increases. So one thing depends on another. Calories depends on how much you walk. So the calories is the dependent, and time walked is the independent. So we have a graph below. It says the graph below represents the height of a tsunami as it approaches the shore. And we want to describe in words what's happening. So it looks like I have two axes here. One is a time axis and one is a height. And it looks like as time gets greater, the height gets greater. So we just say that in words. As time increases, height increases. And I can break that down into dependent and independent variables. The height depends on the time. So we can apply that to our previous examples. We want to identify the graph that shows the relationship between the number of cookies and the equivalent number of dozens. So again, we have two axes, one being the number of dozens, the other being the number of cookies. This says as my dozens increases, my number of cookies goes down. Well, that doesn't make any sense. As I get more dozens, my number of cookies should go up. And that's right here. Notice this graph says as my number of cookies increases, right, or as my dozens increases, so far my number of cookies increases, but it falls apart here. My dozens increase, but my number of cookies is going down, so that just kind of throws that whole thing off. All right, functions. Function is basically a relation such that there's exactly one output for every input. And we want to try, I have three examples here. Here's example 1, example 2, and example 3. And we want to determine if each of these is a function. So it says there's one output for each input. So for the input of 4, do I only have one output? It appears so. For the input of 6, do I only have one output? Yes. For the input of 10, do I only have one output? Yes. For the input of 12, do I only have one output? Yes. All right. Notice I said yes to all these, but I have 3 of the outputs being the same. But notice what the definition says. For each input, there's exactly one output. So there's only one input of 4 and only one output for that input. So this is a function. Notice, for every x value or input, there is only one y value associated with it in this graph. So this is also yes. Now where this falls apart is in this example. Notice, for an input of x, I have an output of 4 and 5 for the input of -1. So in this first number, this already falls apart. This is no. For the input of 0, I get one output of 7. For the input of 2, I get one output of 5. For the input of 1, I get one output of 6. I think it's somewhat easier to see in our next example. When I have inputs and outputs, those are relations, those are ordered pairs. If you take and graph every ordered pair, you get some kind of picture of what's going on. And if a relation is a function, you can use what's called a vertical line test. And it basically says if a vertical line can intersect the graph of a relation in more than one point, it's not a function. So what I'm going to do here is I'm going to take, here's a set of x and y points graphed. And if I were to draw a vertical line through anywhere in that graph, it only crosses one point. It never crosses two. Therefore, yes, this is a function. If I draw a vertical line through any point in this graph, you'll notice each of these cross twice. So no, this is not a function. Likewise, draw a vertical line through here, and they also cross twice. So no, this is not a function. I think the vertical line test is the easiest way to tell if a relation is a function. Now we want to determine if the relation below, in this case an equation, is a function. And the only way to do that is to take and graph that. So what we need to do is we need to pick a bunch of inputs, get a bunch of outputs, graph those, and see if it appears to be a function. In other words, for every input x, is there exactly one output y? So let's go ahead and just pick some random numbers. 0, keep them small, 1, 2, and well, let's go 3. When I plug a 0 in for the x value, I get 4 times 0 minus 1, or -1. So that's the point, 0, -1. When I plug a 1 in, I get 4 times 1 minus 1, which is 3, giving me a point 1, 3. 4 times 2 minus 1, 7, 2, 7. 4 times 3 minus 1, 11, 3, and 11. So I'm going to take and graph these points. Here's 0, -1, 1, 3, 2, 7, 311. And it appears, I mean, if I were to keep doing this forever, it appears that these are unique points. So if I drew a vertical line through each one of these, it appears that this is a function. Alright, now we're going to talk about function notation. We've already done some problems where it says, if I have the equation y is equal to 6x plus 2, I want to evaluate that if x is equal to 4, in which case we'd say y is equal to, making a substitution, 6 times 4 plus 2, or y is equal to 26. All well and good. Done that before. Now over here, this is what we call function notation. We read this term as f of x, or the function of x. In other words, whatever it's equal to is in terms of x. And it says evaluate f of 4. Well, notice what I've done. Rather than saying f of x, I now say f of 4. So I've substituted 4 for x, which basically tells you that in this equation, I need to substitute 4 for x. So it's the same problem as before. I take 6 times 4 plus 2. But in this case, rather than saying that equals y, I say that equals f of 4. So f of 4 is equal to 26. It's just a different way of writing it. No need to freak out. So in this case here, here's an example. I have a new function f of x equaling 3x squared minus 5. And I want to find, once again, f of 4. So what I'm going to do is say f of 4. Notice x has been replaced by the 4. Is equal to 3 times, rather than x, I say 4, squared minus 5. Order of operations says we do exponents first. So that's 3. 4 squared is 16 minus 5, which is 48 minus 5, or 43, which is equal to f of 4. That's all we've got. Here's the first two questions, and the third is directly below it. Answer those, fill out the lesson summary, and we'll talk about it more tomorrow.